We spoke quite a bit about linear transformations in the previous video, but in this video we're going to see how linear transformations relate to conventional matrix algebra. So let's begin with some vector space over a field of scalars, let's say the real numbers for now, but it could be any field. And suppose we have a basis for the vector space. Recall what a basis is. It's a set of linearly independent vectors, let's say E1, E2, E3, which also spans the vector space in question, which is to say any vector in V can be represented as a linear combination of the basis vectors, which is just what it means to span a vector space. And remember what a linear combination is? If we have some vector, let's say V, this can be represented in the basis as a sum of scalar multiples of these basis vectors. For instance, V might be able to be written as V1 E1 plus V2 E2 plus V3 E3, where V1, V2, and V3 are just scalars. They're in that set R. So I have my vector V written as a linear combination of the three basis vectors. But suppose we have some linear transformation, let's say F, which is going to act upon that vector V. So what is F of V? Well, that's going to be F of the right-hand side here, F of V1 E1 plus V2 E2 plus V3 E3. Now remember those properties, the defining features of the linear transformation, which is that we can break it apart over addition and remove scalars and put them out front. So we apply both of those rules here, and this is going to be equal to F of V1 E1 plus F of V2 E2 plus F of V3 E3, but then we can yank the scalars out front, and so we can write this is equal to V1 F of V1 plus V2 F of V2 plus V3 F of E3. So we're just using our knowledge of what constitutes a linear transformation. But there's something very important to note here. That if V is any arbitrary vector, V1, V2, V3 are just those scalars sitting out front of the three basis vectors. That is to say, the components of V in this basis. Let me call this basis B. The components of V in the basis B. But F of V can be calculated if we know how F operates, how F acts on each one of these three basis vectors, irrespective of what the particular components of that vector are in this basis. In that it suffices to characterize the linear transformation if we know how this linear transformation acts on each of the basis vectors. In this case, each of the three basis vectors. To say it another way, if we know what F does to E1, and we know what it does to E2, and what it does to E3, that suffices to characterize the linear transformation completely. Since V1, V2, and V3 were just arbitrary linear combinations of those basis vectors. So that insight that to characterize F completely, it suffices to know how F operates upon each of the basis vectors is a very important one that we have to keep in mind for matrix algebra. Now, we also take note that each one of these vectors here, F of E1, F of E2, and F of E3, can also be expanded in this basis, E1, E2, E3. Let's suppose, just for simplicity, that F was just some map from V into the very same vector space. And we have a basis ready, which spans the vector space. So each one of these, F of E1, F of E2, and F of E3, is just some linear combination of E1, E2, E3. Just something times E1, something times E2, something times E3, where those three somethings would be the scalars, of course. But for computational purposes, we often like to keep track of how F operates on each one of these basis vectors. And what we can do is consider an array of numbers. And in the first column, we just write down the components, that linear combination of E1, E2, E3, of whatever comes out of this, F of E1 in the first column. So it's going to have three numbers, it can be 1, 2, and 3. but we'll get to that step in a second. But let's just write that in the column. We'll do the same for f of v2. That'll form the second column of this array. And also for f of v3, that'll be the third column. So you can see that the first column records how f operates upon e1 and lists the coordinates in this basis. The same for f of e2. It lists the coordinates of f of e2 in the basis b. And similar for the third column. So we have the first column, second column, and third column recording how f acts upon the first, second, and third basis vector respectively. And what I'll do is simply define one of these mathematical entities, which is a listing of columns, each of which gives the components of f of e sub j for the jth column in the basis b, and therefore an array of numbers like this. I'll just call this a matrix. And what we're looking at here would be the matrix associated with the linear transformation f and in the basis b, or with respect to b, because each one of these, when you actually list out the components, is going to be some linear combination of the basis vectors. So we dealt with the example where the dimension, or the number of basis vectors of the vector space, was equal to 3. But so let's remove that stipulation though and just consider some finite dimensional vector space, which would be n dimensional, so n basis vectors. So again, let's say I have some vector space v over the field of real numbers, which are going to be the scalars. And let's say I have some basis b, which is going to have vectors, let's say e1, e2, dot, 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 all the way up to en. So this vector space is going to be n dimensional. And let's just repeat the procedure that we did in the previous slide. Let's say I have some vector v, and I want to expand this in the basis. We have v1 e1 plus v2 e2 plus v3 e3, and so on, all the way up to the last basis vector, which is going to be en, so vn en. And of course, what I'm going to do here is going to collapse all this using sigma notation. So we have the sum, let's say j is equal to 1 up to n of v sub j e sub j. And again, let's operate upon v with f. So we have, consider f of v. So it's going to be f of the sum over j of v sub j e sub j. And we know that f, it's a linear transformation by assumption. This is going to break apart over addition. So the sigma notation can be moved to the front. So this is the sum over j of f of v sub j e sub j. And we also know, because of the linearity of f, that these scalars can be moved out front for each term in the sum. So we can write this the sum over j of v sub j f of e sub j. And again, we see that to totally characterize the linear transformation, how it acts upon any arbitrary vector, it suffices to know how f operates on each one of the basis vectors. In this case, those ones ranging from the first up to the nth. And again, we simply record these vectors, expand them in the basis to get the individual coordinates, and list those vectors as the columns of an array, like this. So we're going to have, in the first column, we're going to have how f operates upon e1. That's going to be the first column. Next column over, we have how f operates upon e2, all the way down, where the components are, of course, listed down the column, components in this basis. And then we go all the way over to f of en, and that forms the last column. And again, we suppose that f is just some map from v to v. So we see that we're going to have n columns in this array. And this is going to be the matrix associated with F with respect to the basis B. Now let's go one step further and consider that array, that juxtaposition of columns, and represent each one of these column vectors as a linear combination of the basis vectors, as we can do, because these vectors are just going to be outputted to, let's say, V, and because B is a basis, everything in V can be represented as a linear combination of these basis vectors. And that applies just as well to these column vectors. So let's move over here. Suppose I consider f of E1 first. As I said, this is going to be some linear combination of the basis vectors. It's going to be something times E1 plus something times E2, dot, 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 plus something times En. Now, what I'm going to do is I'm going to adopt a little bit of notation, but the notation is going to tie directly into matrices. Now, I'm going to call these components, these scalars that sit out front, I'm going to notate them in the following way. It's going to be F, but in the right-hand index, I'm going to just repeat that 1 there to represent how f acts upon E1. And the left is going to be pertaining to the first component. So you can read this as the first component of f of E1. That's what the 1, 1 means. So we move over to the next one. This is going to be the second component of f of E1. So the second component, so the E2 there, second component of f of E1. And so forth. We would have f31 times E3. And then we go all the way up to the nth component of f of E1. So N1. So this wouldn't be, obviously wouldn't be 11 or 21. It would be 1, 1, 2, 1, 3, 1, dot, 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 N1. And just to gain some familiarity with the notation, so f of E2, this would be the first component of f of E2 times E1 plus the second component of f of E2, so 2, 2 times E2, dot, 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 plus the nth component of E2 times En. So that's how I'm going to notate each one of those expansions in the basis B. And what we're going to do is just consider this first column and just write down those components. So we had F11, F11, then we have F21 next. F31 would be next, and we go all the way down to Fn1. So you can see what I'm doing. I'm just taking this first column and expanding it out and writing the components there along the column. So F11, F21, all the way down to Fn1. And we do the same for f of E2. So we have the first component of f of E2. Next down, we have the second component of f of E2. We have F32, the third component of f of E2, all the way down to f of the nth component of E2. And you can see what's going on here. We go all the way over. This over here would be the first component of f of En. Then we have the second component of f of En, all the way down to the nth component of f of En. Just complete that there. Now, if you know anything about matrices and matrix algebra, you'll note that the notation that we've adopted here is extremely convenient for understanding these elements in the array with respect to the rows and the columns of the matrix. In that if we look at these two indices, for example, 2, 1, we can easily read this off as the entry being in the second row in the first column, and that's captured by the notation 2, 1. F21 means in the second row and in the first column. And we may generalize this to interpret anything of the form Fij. So this will be some entry in the ith row and in the jth column. Now, since it's in the jth column, it's going to have something to do with how f operates upon e sub j. And since it's in the ith row, it's going to be the ith place down. It's going to be the ith component of f of ej when this thing is expanded as a linear combination of the basis vectors in B. So that's how you read these matrix elements. Now let's use this notation that we've developed for writing down the elements of a matrix and return to our linear transformation f and see how it operates upon the vector v. So what we're going to do is, again, express v as a linear combination of the basis vectors. So it's going to be sum over j, v sub j, times e sub j. And since f is a linear transformation, we may move the sigma out front because the linear transformation is additive, and we may move the scalars out front, and we therefore have the sum over j, v sub j, times f operating on e sub j. Now, we may expand f operating on e sub j, which is just going to be the jth column. For instance, if this were f of e2, this would just be the second column of this matrix here, the matrix associated with f with respect to the basis b. And we may also represent that as a linear combination of these basis vectors. And here's how we're going to do that. So we just leave that v sub j alone. We have the sum over I this time of f ij. So we're going to have the ith component of e sub j. And since it's the ith component, this is also going to be e sub I. So this here is just the expansion of this written as a linear combination of the basis vectors. So sum over I of f ij times e sub I. Now, since v sub j has no i's in it, we may move this back in here. And v sub j and fij are just scalars, so we may commute those. So what we're left with here is sum over j, sum over I. And it goes without saying that i's and j's are going to be summed from 1 to n. Just abbreviating here. Fij, v sub j, e sub I. And remember, this is equal to f of v. This is how f operates upon v. And one last thing we may do to this double sum over here is we may write that f of v is equal to the sum over I, sum over j, just reversing the order of summation, which we can do, of fij, v sub j, e sub I. And this formula here is a formula for how one takes the product of a matrix with a vector, namely a column vector. So this double sum here gives us the procedure for how to multiply such an array of numbers, a matrix, with a vector whose components are listed out with the v sub j's. Now to see this, let's sum over I first, and consider the case when I equals 1. So what this would be is the first component of f of v. So I is going to take on the value 1, so there'll be e1 there, and what we're looking to calculate is the coefficient, the scalar sitting out front of e1. So this would be the first component of f of v. So we're going to have sum over j, saying I equal to 1, f of 1j, substitute I equals 1 right there, f of 1j, v sub j, times e1, which when this is expanded out, sum over the j's, so we have f11 v1 plus f1, because we keep the 1, 2 v2, next to be f13 v3, dot dot dot, all the way up to f1n vn, and then this would be times e1. This whole thing is going to be the coefficient sitting up front of E1. And if you look at what this is corresponding to in the matrix up here, so we have F11, F12, F13, and so forth. We remain in the first row and move through each column. So we have first row, first column, first row, second column, first row, third column, all the way up to first row, nth column. Those are the left-hand factors here, there, and so forth. Then we have V1, V2, V3, and so forth. And this corresponds to what you normally do when you take the product of a matrix and a column vector, in that you may write the vector like this, V1, V2, dot, 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 all the way down to Vn. And this is why that sort of multiplication works. We have F11 times V1, then F12 times V2, F13 times V3, all the way up to F1n times V sub n. Add those together, and what you get out of that is the first component of the resultant vector, which we're calling f of v. So what we have is the formula for how to multiply a matrix and a vector. This is why all that stuff works. So what you aim to do is set up your matrix algebra and vector algebra when you do the computations in such a way that it reflects what's going on with linear transformations, which is what we've seen in that previous example. So that formula comes from just thinking about linear transformations. And other things that we'd like to do with matrices would be, for example, to scale them, add them, and multiply them in the sense of composing them. So let's check and make sure that the conventional formulas for how you multiply, add, and compose matrices actually work in the way that we think they do, just from thinking about linear transformations. So first, let's consider not the linear transformation f, but some scalar multiple called lambda times f. And let's consider how that operates upon this vector v. And we'll do what we've done before. We just expand all this out. But remember that this thing equals lambda times f of v. That's just what it means to take the scalar multiple of the linear transformation. And let's ask what the matrix representation for lambda f is, given the matrix representation for f. If we know the matrix representation for f, what should be the matrix representation for lambda f? Now, what we've got here is lambda times f of v. Now, we've been through the work of seeing what f of v is once you expand everything out, so we'll just copy that down. So we had sum over I, sum over j, f of ij times v sub j times e sub I. Now, we simply bring this lambda right in there, since it has nothing to do with the i's and j's, it's just a constant. So we have lambda times f of ij. I'll throw some parentheses around that because I can. F sub j, e sub I. Now notice this line is in the same form as here to here for the matrix representation of the linear transformation, in that we have a double sum of some scalars here times v sub j times e sub I, except that this is going to be the matrix representation in question. So this is going to be the matrix representation for the scaled linear transformation lambda f. So this would be lambda f I sub j. And therefore what we've shown is that if we know the matrix representation for f ij, then the right matrix representation for lambda f is given the following way. Lambda f I sub j, the ij entry of this is simply given by lambda times the ijth entry for f, as you would expect. So if you had a linear transformation and you want to consider, say, 2 times that, the matrix that represents that is simply 2 times the original linear transformation. You just scale each of the entries of the matrix by that scalar multiple. Very simple. So this is how you appropriately scale a matrix such that it still conforms to what's going on with the linear transformation. We may also prove a similar sort of thing for the sum of 2 linear transformations. Suppose I have now two linear transformations f and g, and I consider the sum linear transformation f plus g, which we know from the last video is a linear transformation. So what should be the matrix representation for f plus g given the matrix representations for f and g by themselves? So how does this act upon v? As we discussed in the last video, this by definition is f of v plus g of v. And we may expand this term and this term out as we've done down here. For this term, g of v just replaces f by g. So what we have here is going to be the double sum over I, also over j, of f ij v sub j e sub I plus g ij v sub j e sub I. Now, of course, we may do a little rearranging here, and we may write fij plus gij times vj e sub I. Now notice here, as in the previous case, we have something of the right form for the matrix representation, and that we have a double sum of some scalar times v sub j e sub I. So this thing, this scalar here, is going to be the ij entry of the sum linear transformation. So it's going to be f of g, f plus g, the ij entry. So the matrix representation of the sum is given by simply the sum entry-wise of those two linear transformations. So if we want the ij entry in the matrix representing f plus g, you simply take the ij entry in f and add it to the ij entry in the matrix g. So you just add entry-wise, as you're probably used to when you add matrices. But this is why that works and why it corresponds to linear transformations. So we've examined how we scale matrices, how we add matrices, and the last thing to check is how we compose or multiply matrices, which corresponds to the composition of two linear transformations, which again we proved in the last video was also a linear transformation. So let's say we have two linear transformations, f and g. We now ask, what is the matrix representation for the composite transformation fg? We use the same procedure. We operate upon it, operate upon v. This by definition is f of g of v, as we defined in the last video. Let's consider g of v first, which we already know. This is going to be the double sum over I over j of g ij v sub j e sub I. Now, we may use the linearity of f to not only remove those two sigma notations, which signify addition, we may also remove the scalar and the scalar. So what we're going to be left with is sum over I, sum over j, gij, v sub j, and then f of e sub I. Now the next thing we're going to do is note that this f of e sub I is going to be some vector, but this vector, like the vector v, can be expanded in the basis. So what we're going to have is yet another sum. I'm going to let that be the sum over k, since that's one index, that's one letter we're not using. So now we're going to have the sum over k. Now this time we're going to have f. So we're going to get the kth component of how f operates upon e sub I times ek. Notice that index, that letter lines up with this one lines up with this. Now this is a sum over k. These two factors have nothing to do with k, so they may be brought back in. So we have a triple sum over I, sum over j, sum over k of gij times v sub j f ki e sub k. Now what I'm allowed to do, since all of these are scalars, I may commute them as I see fit. So what I'm going to do is simply do a little rearranging. We have a triple sum here, but what I'm going to do is also flip the order of summation. I'm going to have the I there. I'm going to place the k over there and the j here. And what I'm going to write is fki gij v sub j e sub k. Now, this is also in the right form, as we have been saying before. We have a double sum of some scalar, and the right scalar is actually going to be confined by those parentheses there, times v sub j times e sub k. Except the letters are slightly flipped, but the letters don't really matter. So what we have here, let me move this up here. This is going to be the sum over the i's. V ki g ij. This is going to be one of the matrix entries for fg. But which one is it? So we're summing over the i's. And what is left is going to be kj. So this is going to be the kj entry of fg, which is the composite matrix, which is given by that summation there. So to find the kj entry, you have to place the k there, the j there, and to sum over the i's in this manner, which we're going to examine in a second, which is going to correspond to how you've probably learned to multiply matrices, but this is why it works. Now, if you're really confused by the letters here, in that why is the I being summed over, whereas we had I sitting out front here, these letters are totally arbitrary. You can change the letters as you see fit. What's important is the structure, the form here. So to make this a little bit clearer, what you can do is just flip the letters K and I around. Where you see a K, replace it with an I. Where you see an I, replace it with a K. And so we may write this formula in a perhaps more familiar way, which is that the ijth entry of fg is going to be given by the sum over k of f I k. Remember, replace the k with an I, replace the I with a k. G k j. So that's probably a more familiar form, just in terms of the conventional letters. But as I said, it's a structure, the form, not the letters themselves, that are important. So what we've derived here is the correct formula for multiplying matrices such that they correspond to what's going on with linear transformations. In the case of these matrix multiplications, it's what's going on when we compose linear transformations. And that fg is going to represent the matrix that represents the composite linear transformation f of g acting upon some vector. Now, how do we understand what this sum means? For instance, let's say I want the 1-2 entry of fg. What do I have to do? Well, I have to sum over k, letting I be 1, j be 2. So this would be f1k, gk2. And you just expand out with the sum as you sum over the k's. So this would be f11, g12, plus f12, g22. So you can see it's the inside indices that are changing because that's where the k is. So it'll be f13, g32, dot, 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 all the way up to f1n, gn2. So that would be equal to the 1-2 entry in the matrix fg. And you can see what's going on here. f11 is the first row, first column. Then how do we get to f12? Well, you go over to the second column, you go over to 1, 3, and so forth. But what's going on with these ones? So we have G1, 2, so first row, second column, and then we go down to the second row, second column, then third row, second column, so you go down the rows there. So this corresponds exactly to how you probably learned to multiply matrices. But the point is, this is why that matrix multiplication is set up in precisely the way that it is, because we want the matrices to represent linear transformations, and this is the way the entries must be multiplied in order that they may represent linear transformations. This is why matrix multiplication is defined in the way that it is, as opposed to, say, multiplying entry by entry. But if you do that, it doesn't represent a linear transformation, at least not necessarily. But this is the right way to multiply matrices, such that they represent what's going on when we compose linear transformations, which is all the stuff we were doing over here. So we derived the right way to multiply matrices such that they correspond, that they conform to what is going on when we compose linear transformations. Now you may have noticed that the matrix that represents a linear transformation, the precise entries that go into the matrix are going to depend upon the basis that's chosen. So if we have a different basis, we could have the very same linear transformation, but the matrix that represents it, because the basis might be different, might have different entries. And to see that, we're going to take a concrete example, simple example in 2 dimensions, which is going to be the rotation counterclockwise by 90 degrees. So rotation counterclockwise by pi over 2 radians. And this, as we showed in the last video, this is a linear transformation. Now let's set up 2 frames, or 2 bases. Let's say this is going to be the standard basis, which I'm currently notating as E1, E2. Now let's set up a slightly different basis. Let's suppose we have this other vector here, which I'm going to call E1 prime, which is going to be the sum E1 plus E2. And then we have a second vector, which I'm going to call E2 prime, which is going to be -2 times the length of E2. So this will be E2 prime. So we have 2 bases here. We have the basis consisting of the set E1, E2. So let me write that. So basis is going to be E1, E2. But then we have a second basis, which I'm going to call B prime, which is going to be the E1 prime, E2 prime set. Now let's think about this linear transformation, this rotation, which I'm going to call R. So we'd like to know what the matrix entries of R are going to be. Let's think of this first basis first. So let's ask, what is R of E1? Because remember, it suffices to totally characterize the linear transformation if we know how it acts upon each of the basis vectors. So let's do precisely that. What is R of E1? Then once we know that, we're going to stick down the first column of the matrix. We see that E1 is going to be rotated 90 degrees, and it's going to go up to that vector there, which is E2. What are the components? What is the linear combination in this basis? Well, it's 0 times E1 plus 1 times E2. So in the basis B, we know that the first column is going to be 0, 1. Let's ask what happens with R E2. So RE2 is going to get rotated over there. Let me see if I can draw that in. And what is that in the basis B in terms of a linear combination? Well, that's simply -1 times E1 plus 0 times E2. So it's going to be minus E1 plus 0 times E2. Therefore, the second column of this matrix is going to be -1, 0, because those are the coordinates in this basis. So this matrix represents the linear transformation R in the basis B. So this would be So it'd be in the basis B. But let's do that very same procedure with the basis B prime. So let's look at the basis B prime. And let's ask, what is R acting on E1 prime? Let's look at E1 prime. That's going to get rotated 90 degrees. So that's going to go over here. So that'll be R of E1 prime. This should be an R down there. Those are right angles. But what is this vector expressed as a linear combination of these two vectors, expressed as some multiple of this plus some multiple of that? To find out which one that is, we simply project like so. We draw a line parallel to E2 and we project it onto this line, which is the span of E1 prime. So we find it's going to be that vector down there, which is just minus 1 E1. So we have minus 1 E1 prime. And then we want to project upon E2 prime. So what we're going to do is draw a line parallel to E1 prime such that it touches the line in the span of E2 prime. So that's actually going to be up there. What is the vector from here to there? Well, that's just negative E2 prime. So what we have is minus E2 prime. So basically you can see that if we take this vector and add to it this vector, then we get that vector. So that's simply this vector expressed in a different basis. But what are the coordinates there? It's minus 1, minus 1. Therefore, the first column, R of E1 prime, is going to have entries minus 1, minus 1. Now, what is R E2 prime? E2 prime is over here. And when we rotate 90 degrees, it's going to come over here. That should be R of E2 prime. And what is this going to be in the basis E1 prime, E2 prime? So we use the same procedure as before. We trace parallel to E2 prime such that it touches there. So this is going to be 2 times E1 prime when you actually do the computation. And you can see that it's approximately 2 times E1 prime there. And then we need to project onto E2, and we draw a line parallel to E1 prime. And when you do that, it should actually be exactly on there. So this is going to be plus E2 prime. It should be directly there if you do the computation. What are the components? We have 2, 1. So this is the matrix representation for a rotation of pi over 2 radians counterclockwise. And you can see clearly that the entries in those matrices are different. But the reason they're different is because we've chosen 2 different bases. This is the representation of that very same linear transformation in this basis. This is the matrix representation for that linear transformation in this basis. So the entries of a matrix, when they represent a linear transformation, are basis dependent. Now, one interesting question you may ask is that if I have this matrix, let me call this matrix R, which represents a linear transformation in the basis B, can I figure out from that, and perhaps given another collection of matrices, can I figure out what this representation is? Let me call that one R prime, which represents the very same linear transformation but in a different basis. Can I convert the entries of this matrix into the entries of that matrix, and how should I do that? Well, the way to do it is to recall the relations between these two bases. And this is going to be the so-called change of basis topic in linear algebra. But it's easily conceptualized once you remember what's going on here in terms of linear transformations. So remember how we set up E1 prime and E2 prime. So E1 prime was simply the sum of E1 and E2. E2 prime was minus 2 E2. So those are relations between the primed basis and the unprimed basis. And if you just do a little rearranging here, you'll see that this system is equal to E1 equals E1 prime plus 1/2 E2 prime, and E2 is equal to minus 1/2 E2 prime. So let's suppose that I have some vector expressed as a linear combination in this basis that has coordinates in this basis. So let's start with V coordinates in B prime. Now suppose I had some transformation that would convert the coordinates in B prime to the coordinates in B. Well, if I can do that, that's convenient because I already know what the correspondent matrix representation of the linear transformation is in this basis. And then I could apply the linear transformation, which we're calling R here, and this would be f of V coordinates in B, in that very same basis. But then I want to convert back to coordinates in the basis B prime. So I need some linear transformation which is going to take the coordinates in B to the coordinates in B prime, which is actually going to be the inverse of this transformation, whatever that is there. Now traditionally this one is called P, and this one's going to be P inverse. You can see this P is mapping coordinates in B prime to those in B. This is doing the reverse. It's mapping B coordinates in B into coordinates in B prime. So this would be, at the end of the day, f of V coordinates in B prime. Now, what is the composite of all of this? Well, we start from here. So we have P, then R, then P inverse. And this, I claim, is going to be the matrix R prime. The only thing that's really left to do is to take a look at what this matrix P is, and from that we may compute its inverse as well. But this is going to be the central formula that you're going to see when you talk about the topic of change of basis. And also on this diagram that I've drawn in below, make sure you take note of what the composite action is when we go from here directly to there, which is going to be precisely P inverse R P. So we take V with coordinates in B prime, and we map it to f of V coordinates also in B prime. So make sure you understand what's going on in this scheme below. Now, what should this linear transformation be for P? Because this mapping of coordinates is also going to be a linear transformation. So what should be in, for example, the first column of this matrix P? Well, what this is going to be is that first column is going to tell me what the coordinates in the B basis are going to be for the vector E1 prime. It's going to be this vector here. So what are the coordinates of this vector in this basis, E1, E2? Well, it's easy to see, not only from the diagram, but from the definition. What are the coordinates? 1, 1. Therefore, the matrix P is going to have in the first column 1, 1. And what does E2 prime get mapped to in the basis B? We can see down here, and by the way it was defined, That's minus 2e2. Therefore, the second column is going to be 0, minus 2. So very simple. That's the matrix P. Now, to find P inverse, which is going in reverse, it's mapping coordinates in B to coordinates in B prime. We can either do a little computation and calculate what the inverse matrix is going to be, or we can use very similar reasoning for P inverse. And we just look at the setup here. So what is E1 in that B prime basis? Well, we look at the coordinates, 1, 1/2. 1, 1/2. That goes in the first column there. How about the second column? What's E2? Well, it's going to be 0, minus 1/2. 0, minus 1/2. And that's it. That's B prime. So this matrix here takes coordinates in B prime and maps them to coordinates in B. This takes coordinates in B and maps them to coordinates in B prime. And we may check to see that R is converted to R prime by this computation P inverse RP. What we're going to do is, we've got P inverse right there, so let's multiply by R, which was 0, 1, minus 1, 0. Now we've got P over here, 1, 1, 0, minus 2. So this is going to be P inverse RP. This is equal to, let's multiply this matrix by this matrix. I have 0, 1, so I'm going to take 1 of the second column, 0 minus 1/2, then minus 1, 0, so minus 1 of the first column, minus 1, minus 1/2. Then we have 1, 1, 0, minus 2. 1 of the first column, 1 of the second column, so we just sum the columns. Minus 1, minus 1. 0 of the first column, minus 2 of the second column, which is 2, 1. Which is indeed equal to R prime above. Now, there's something very interesting to know about these two matrices, R and R prime, with respect to their determinants. Now, you may already know from your own studies, or perhaps from a previous video in this series, that when you have a 2x2 matrix, the way to compute its determinant, many ways to compute it, many ways to think about it. You can think of it as this times this, minus this times this. Either that or the wedging of the columns, which is the way I encourage you to think of it. What's the determinant of the matrix R here? That R is equal to 0 times 0 minus 1 times 1, which is minus 1. Which makes sense. We've proved that already, that the determinant of a rotation is equal to 1, and that, in this case, the areas are unchanged both in magnitude and in orientation by a rotation. What is the determinant of this matrix? What is det R prime? Again, just computing it directly from the entries of the matrix. We have minus 1 times 1, so we have minus 1 minus minus 2, so minus 1 plus 2, which is also plus 1. So the determinants of these matrices are the same. Now, that's not just a coincidence in this case. We're going to prove that in just a second. Now, this is one invariant associated with a linear transformation. This is intrinsic to the linear transformation itself. That's the superior way of thinking of this. And either matrix representation in either of these bases is going to reflect that. That it doesn't matter what basis you choose to represent the linear transformation, because it's going to preserve the determinant, because the determinant is something intrinsic to the linear transformation itself, because it relates to the way in which it scales areas or volumes or n-dimensional volumes with respect to their orientation and also their magnitude. So the point is, the determinant of a linear transformation is basis invariant. It does not change depending upon your choice of basis. Another invariant with these linear transformations, something I won't go into too much detail in this video, is called the trace of a linear transformation. And the trace, in terms of the matrix entries, it's very simple. It's the sum of the entries down the diagonal. So in this case, it's 0 plus 0. So the trace of R is equal to 0. What is the trace of R prime? Well, it's the sum of the entries down the diagonal, so minus 1 plus 1, that's also 0. Now that's also not a coincidence. The trace is another invariant of a linear transformation. Now why this is also invariant is also kind of interesting reason. I won't go into the details in this video, but it has to do with the eigenvalues. The eigenvalues do not change depending upon your choice of basis. Let's prove that statement that we made before, that if R prime is given by P inverse RP, then the determinant of R prime is equal to the determinant of R. It's very easy to do based on what we proved in the last video, that you can split up the determinant over multiplication. So the determinant of R prime is equal to the determinant of P inverse RP, which is equal to the determinant of P inverse times the determinant of R times the determinant of P. What's the determinant of P inverse? Well, that's 1 over the determinant of P. Then we have determinant of P times determinant of R. Those are scalars, so I can just commute. Those are reciprocals, and we're left with, on the right-hand side, the determinant of R is equal to the determinant of R prime. Now this should, again, make total sense because the determinant of a linear transformation is intrinsic to the linear transformation itself, and it does not matter what basis you choose. It's basis invariant, and whatever basis you do choose, it should be reflected in the matrix that represents that linear transformation. A few last comments I'd like to point out before we close this video. And to make those comments, what I'd like to do is return to some arbitrary vector v and consider f of v once again. And the basis that we're going to consider is going to be an orthonormal basis. So it's going to be sigma 1, sigma 2, and sigma 3. Just going to change up the orientation. I'm going to change up the notation here just to emphasize the orthonormality of this basis, and sigma is usually chosen to emphasize that. So we have f acting on v. So v can be written as v1 sigma 1 plus v2 sigma 2 plus v3 sigma 3, for example. Just to pick n equals 3, this can be generalized, of course. Now this is going to be equal to v1 f of sigma 1 plus v2 f of sigma 2 plus v3 f of sigma 3. So again, we see f acting upon each of the three basis vectors there. In this case, the basis vectors are orthonormal. That is to say, they're mutually orthogonal, and they're all of length 1. So f of sigma 1, once in turn represented in the basis, is going to be the first column of the associated matrix that represents the linear transformation f. But what I'm going to do here is I'm going to consider f of sigma 1 for a second. And we can actually do something pretty interesting because we're representing everything in an orthonormal basis. So I'm going to expand this out as a linear combination of sigma 1, sigma 2, sigma 3. So again, this would be the first component of how fx upon sigma 1 in this case. This would be f11 of sigma 1 plus the second component of how fx upon sigma 1, sigma 2. Then the third component of how fx upon sigma 1, sigma 3. Now, suppose I want to solve for, let's say, this entry. I want to solve for that entry. What can I do here? Well, if I dot both sides with sigma 2, watch what happens. So we have f sigma 1, and I'm going to dot with sigma 2. So we have f11 sigma 1 dot sigma 2 plus f21 dot sigma 2 dot sigma 2 plus f31 sigma 3 dot sigma 2. Now, since the sigmas are orthonormal, this term and this term go to 0 because sigma 1 and sigma 2 are orthogonal. They dot to 0. Sigma 3, sigma 2 also dot to 0. This term is simply the squared length of sigma 2. Its length is 1, so this is 1. What's left on the right-hand side is precisely the component that I want, f21, which I found is equal to sigma 2 dot f sigma 1. Now, the fact that this is 2, 1, and this is 2, 1 is no coincidence, because we're going to generalize this process in just a second to isolate an arbitrary ij entry from a matrix. But another piece of notation before we do that, if we take sigma I, where I can be any number, and we dot it with sigma j. Now, if I is not equal to j, this could be something like sigma 1, sigma 2, sigma 1, sigma 3. If I is not equal to j, they're going to be orthogonal, which means they're going to dot to 0. So this dot product goes to 0 if I is not equal to j. The alternative is if I is equal to j, then we have sigma 1 dot sigma 1, which is equal to the squared length of sigma I. And since these are of unit length, this is going to be 1. So this whole thing on the right-hand side, 0 if I is not equal to j, 1 if I is equal to j, is symbolized in a very convenient notation, delta ij. This is called the Kronecker delta, and this thing evaluates to 0 if those two indices are different. If they are the same, then it's evaluated to 1. But this is a very convenient way to represent such a situation here where we have dot products of orthonormal vectors. So let's suppose I'm interested in the matrix entry Fij. And I'm representing that in my orthonormal basis with n vectors. And if I'm interested in Fij, let's consider f of sigma j. How does f act upon sigma j? I represent that as a linear combination of my orthonormal basis vectors. So this will be f, the first component of how f acts on sigma j, so f1j, sigma 1 plus f2j, sigma 2, dot dot dot, over to fnj, sigma n. And of course, I'm going to collapse this down using some sigma notation. This would be k going from 1 to n, fkj sigma k. That's equal to f of sigma j. Now, I'm interested in the ij component, so what I'm going to do is I'm going to dot both sides by sigma I because I'm interested in the ij component. Dot product is commutative here, so it doesn't matter if I do left or right. So what I'm going to do here is keep the k. So we have fkj. Actually, I'll dot that on the left just for clarity. So we're going to have fkj sigma I dot sigma k when that dot product is distributed to all of the terms in that sum. So this is equal to sigma sum over k fkj. Now, what is this? This is going to be the Kronecker delta ik. Now, the sum is over k. Now, remember, this is only non-zero when I is equal to k. When k takes on the value I, that is. So every term in this series is going to be 0 except when k is equal to I. K is equal to I, so we're going to replace that k with an I. So this is going to be equal to Fij. That's going to be that side. So Fij is therefore equal to sigma I dot F sigma j. So this is the expression for the matrix entry Fij in terms of a dot product between sigma I, which is one of the basis vectors in the orthonormal basis, and how f operates upon sigma j. But this should make total sense because, remember, we're thinking of Fij as having something to do with how f is operating upon, in the previous case it was E sub j, but here it's sigma j, and we want the ith component of this vector. And the way we're getting the ith component is simply dot with sigma I. And it's convenient here because it's orthonormal, and it just extracts out the ith component of f of sigma j when it's written out as a linear combination in that orthonormal basis. And as an interesting side note here, suppose f is the identity operator. So we have 1 hat, which is our symbol for the identity operator. Let's ask what the matrix entry is going to be. So 1 hat, the identity operator, the ijth entry, that's going to be sigma I dot the identity operator acting upon sigma j. The identity operator applied to sigma j is simply sigma j. So this is sigma I dot sigma j. But as we've seen, this is equal to the Kronecker delta ij. Now, again, this is only 0. It's 0 when I is not equal to j, and it's 1 when I is equal to j. But what does it mean in a matrix for I to be equal to j? Well, what that means is that this entry would be on the diagonal of a matrix. So that's why the identity matrix is going to have the following form. It's going to be 1s down the diagonal and 0s off the diagonal. Because this is when I is equal to j, and off the diagonal is when I is not equal to j, in which case the Kronecker delta of ij would be 0. Now, given some linear transformation f, let me introduce an associated linear transformation, which I'm going to notate with f bar, which is called the adjoint transformation. And the adjoint is defined in the following way. It's the linear transformation such that for if we have two arbitrary vectors u and v, if we have u dot f of v, this is always going to be equal to f bar u dot v. So the adjoint f bar is defined in the following way. It's related to f in the following way. And you can see just what's going on here. You have the uv in the same order, but then the f is getting moved to the opposite vector to operate upon that vector. And the linear transformation is such that you can do this for any arbitrary vector u and v. It's called the adjoint. Now, why do we bother with such a thing? Well, one reason we bother with such a thing can be seen with just looking at the matrix entries of this. What is going to be the ijth entry of f bar? Well, we just use a similar form here. So this is going to be sigma I dot f bar sigma j. But now we just use that property of the adjoint where we can move that over here. That's going to be equal to f acting on sigma I dot sigma j. Now the dot product can be commuted. We'll assume we're working with real numbers here, so there's no problem with flipping the order. So we have sigma j dot f sigma I. But what is this thing? Well, go back up to this formula. We have sigma j dot f of sigma I. This is the ji entry of the matrix F. So we see that f bar is related to f in the following way. That the ij entry of f bar is equal to the ji entry of f. So you can see that the rows and columns get swapped around here. For example, if I want let's say the 2, 1 entry, if I were interested in that entry, that's going to be equal to f1, 2. So the 2, 1 entry in the adjoint is equal to the 1, 2 entry in the non-adjoint, just f. And again, if you know a little matrix algebra, you can see that this highly suggests that what f bar is, what the adjoint is going to have something to do with the matrix transpose, which is when you swap rows and columns. Now, there's a special class of linear transformations such that f is equal to its own adjoint. A few different names for this. One is that these are called self-adjoint linear. These are self-adjoint transformations or self-adjoint operators. Another name is that they are symmetric linear transformations. Why should we say that they're symmetric? Well, if f is equal to f bar, if we take a look at its matrix entries, we have this is true in general, but if f bar is equal to f, then the left hand side here is equal to fij is equal to fji, in that the ij entry is the same as the ji entry. So the ij's are symmetric, they can be flipped around, and those matrix entries are the same. So there's a symmetry between the I and the J and the I. The order doesn't matter. Now, we may also note that if f bar is equal to f, then this equation becomes u dot f of v is equal to f of u dot v. And you can see if we have the symmetrical linear operator here, we can just move the f to operate upon that vector, and then dot it with v, as we have on the right-hand side. Now, corresponding to symmetric operators, we also have what are called anti-symmetric operators, which is very similar to the case we have here. Instead of f being equal to its adjoint, it's equal to the negative of its adjoint. Equivalently, the adjoint is the negative of f. And such operators are called anti-symmetric. And that taking the adjoint is the same thing as taking the negative of the operator. And the analogous condition here is instead of fij being equal to fji, it's equal to minus fji. And this equation, instead of, as you see here, this would be u dot fv is equal to minus f of u dot v. So you can move it to that first vector, just have to stick in a minus sign for anti-symmetric operators, if f is an anti-symmetric operator. Now, just for special interest, in the setting of complex numbers, there are similar conditions. Instead of fij being equal to fji, if we have complex values here, if we have an operator such that fij is equal to fji conjugate, then such an operator is called a Hermitian operator. Now, these Hermitian operators are of special interest in a few fields in physics, most notably quantum mechanics, because all of the operators associated with physical properties, for instance, momentum, or the energy, in which case we'd have the momentum operator or the Hamiltonian operator, respectively. These are all taken to be Hermitian operators, for the reason that these have a number of special features, in that these operators are guaranteed to have eigenvalues which are real. They must be real numbers, and these eigenvalues are going to correspond to the observed values for whatever it is that you're measuring. And furthermore, if you have two eigenfunctions and they have different eigenvalues, they're guaranteed to be orthogonal. That's also true for the symmetric operator. If you have eigenfunctions or eigenvectors which correspond to two distinct eigenvalues, they're guaranteed to be orthogonal. One last comment I'll make about the adjoint and some of these classes of transformations that we'll study in subsequent videos is regarding the orthogonal transformations. Now, suppose I have two vectors, let's say u and v, and let's say I apply some operator f to them individually, and I take the dot product. Now, if that dot product is the same as the dot product of the vectors before the transformation, such a transformation is called an orthogonal transformation. But let's see, using the adjoint, how this relates to the adjoint and see if there's any special defining feature of these. So let's consider the left-hand side. We use the definition of adjoint to bring this f over there to operate upon that vector. So we have f bar f operating upon u dot v is equal to u dot v. This is equal to f bar f, the composite acting on u dotted with v, equals u dot v. Now, if u and v are just arbitrary vectors, then this thing right here, this operator, must be the identity operator, since it's just 1 over here, where u and v are just arbitrary vectors. So we have the condition for the orthogonal transformation, f, that f bar f is equal to the identity operator, which entails that f bar must be the inverse of f. And that right there is the defining feature of what's called orthogonal transformation. And remember how we set this whole thing up, that the dot product is preserved by the transformation, that if you take the two vectors, operate upon them, consider the dot product, that's the same dot product as the two vectors which were untransformed. Now, such an example of an orthogonal transformation would of course be a rotation, since the rotation preserves the dot product. And also remember that we're talking in terms of operators and transformations here, but each one of these conditions, whether we're talking about an orthogonal or symmetric or anti-symmetric, has a corresponding matrix understanding too. And that this in matrix language would say something like the transpose of a matrix is equal to its own inverse, in which case we'd be talking about an orthogonal matrix. Or a symmetric matrix would be a matrix such that it's equal to its own transpose. Or an anti-symmetric matrix would be a matrix such that its negative is equal to its transpose. So remember to keep that in mind going back and forth between matrices and the linear transformations themselves. So we'll study some classes of these transformations, particularly symmetric linear transformations, in subsequent videos, as I said. And that'll do it for this video. I thank you for watching.